Let's talk about a phenomena or a measure of the probability probability mass function of a random variable that comes from information theory, and that's called entropy of a random variable. So, if you think about the regular term entropy, it hints towards chaos or randomness, right? And that's what we will try to capture for a random variable. A random variable that is already random, how do we capture its randomness? So the idea is being that random variable, the term is a general term that captures any variable whose behavior is not fixed, right? It depends on random variables, but within that, let's say even if we are talking about a coin toss, uh, a fair coin is more random than an unfair coin, than a biased coin, right? So for biased coin, we are actually more sure of one of the outcomes compared to the other outcome. So let's try to capture that, right? So let's say you have a variable x, right? And what we are interested in is capturing its entropy, which is h of x, and this quantity should be high when the variable is more random, and it should be low when it is less random. So the definition of this is that it is going to be negative expected value of log of x, and sorry, log of p of x. Okay, and all logs are natural logs unless stated otherwise. So what does that mean? So this is going to be equal to negative of sum over all x, okay, log of p of x, okay, p of x. All right. So for a Bernoulli random variable, this is going to be equal to minus log of x, okay, and now we are going to take the value log, sorry, not log of x, sum over x, okay, log of 1 minus mu, okay, times 1 minus mu plus mu times log of mu. Okay, so when mu is equal to 0.5, when it is a fair coin, then your h of x is going to be zero point 0.5 times log of zero point 0.5 plus 0.5 times log of zero point 0.5, right? So this is so it is going to be log minus log of zero point 0.5, which is minus log of 1 over 2, which is equal to log 2. Okay, now let's take the other extreme case where mu is either 0 or 1. So let's take limit mu tending to 0. Okay, h of x, it is going to be minus, okay, uh, 1 minus mu log of 1 minus mu, okay, minus mu log of mu. Okay, so now think about it this way, that when you have limit of mu tending to 0, this quantity will tend to 1, right? And log of 1 is 0, okay, and it is being multiplied by 1. On the other hand, this quantity will tend to infinity or negative infinity, but because of the negative sign it will become plus infinity, but it will be multiplied by another quantity that is tending to 0. Okay, so we can apply L'Hopital's rule, and basically what we will get is 0. Okay, so think about it this way: you have two possible outcomes, right? Now this outcome, when both outcomes are equally likely, then there is more chaos, more randomness, so we'll get high entropy. Okay, and so this is what this is x, and this is p of x. On the other hand, when one of them is very small and the other is almost 1, then we will get low entropy. So if we draw the curve of mu versus h of x, what we'll get is low entropy at 0, high entropy at zero point 0.5, and then again low entropy at 1. So this is 1, this is 0, and at the top it will be log of 2. Okay. So when you have both outcomes as equally likely, then you will have high entropy. Otherwise, which means that knowing the outcome will give you a lot of information, whereas when mu is close to 0 or close to 1, then knowing the outcome of the coin toss doesn't give you much information. Sorry, it gives you a lot of information, but uh, uh, let me put it this way: it has less randomness, so you are more sure of what the outcome is going to be. Okay, so in that case, your entropy is going to be low. So until now we have only talked about a single random variable, but now we will talk about more than one random variable, and then we will define something called joint probability. So let's take an example of a dice, right? So your dice can have 6 possible outcomes, right? So let's say you have x belongs to 1, 2, 3, 4, 5, and 6. Okay. Now we define two new random variables. Let's say y uh, is mapping the event that the number is even, okay, to the variable y. So let's say this belongs to 0 or 1. Okay. 0, 0 means even and 1 means odd. Okay. Similarly, let's define another variable z, and let's say that also belongs to 0 or 1. Okay. So here 0 means greater than 3, sorry, less than 3, let's put it less than 3 just to be consistent. Less than 3, the outcome is less than 3 of the dice, this is dice. And then 1 means more than 3. Less than or equal to. Let's keep it that. 1 means more than or equal to 3. Okay. So now what we can do is we can define something called joint distribution over y and z. Okay. What does this joint distribution looks like? It basically, now you can have two different outcomes. Okay. You can have an outcome for y is equal to 0 and y is equal to 1, and then you can have z is equal to 0 and z is equal to 1. Okay. So what is the probability that y equal to 0 and z equal to 0 happen together? So the number is even and it is less than 3. So this is going to be 1 by 6. This is the only way this can happen is if you get a 2. Okay. And what is the probability that uh, the number is greater than or equal to 3 and it is even? So you will get 4 and 6, right? You will get 4 and 6, and basically that is 2 by 6. What is the probability that it is the number is less than 6 but it is odd? That is going to be 2 by 6. Okay. And what is the probability that it is greater than or equal to 3 and it is odd? Okay, so that is going to be 2 by 6. Let me see, where did I make a mistake? So this was our joint distribution table. Okay, and now let's look at some phenomena. Let's look at some other ways of looking at this table. So one thing that we will define is what is the probability of y given z. Okay, what does given mean? So this line is called given. This pipe is called given. What does that mean? If I fix the value of z to be something, then what is the probability of y taking some value? Okay, so let's say if I what is the probability of even given x is even, given x is greater than equal to 3. Okay, that is what I'm asking. So what does greater than equal to 3 means? Greater than equal to 3 means that we are looking at this column. We are looking at this column. Alright. In this column, what is the fraction, relative fraction of y is equal to 0? Alright. So you can see that it is going to be so if this is 2 by 6 and this is 2 by 6, the whole is 4 by 6. What is 2 by 6 as a fraction of 4 by 6? So this is equal to 2 by 6 divided by 2 by 6 plus 2 by 6, which is equal to half, which makes sense, right? Given that x is greater than equal to 3, what is the probability that it is even? And that is going to be half, right? So it can be either 4 or 6. Okay. Uh, so this is defined as follows, right? So basically what you will have is p of y given z, okay, is equal to the joint probability p of y given z, sorry, p of y comma z divided by p of z. This is called Bayes rule, or another way of writing this would be p of y comma z is equal to, not Bayes rule, it's a, we'll come to Bayes rule later. Uh, this will lead to Bayes rule. Okay, this is basically just one of the fundamental expressions in probability. Okay. Uh, so how does that work out? So here what we will have is p of y comma z uh, is going to be so here it is going to be this 2 by 6 divided by what is p of z, that is going to be what is the probability that it is greater than or equal to 6, that is going to be 4 by 6, which comes out to be 1 by 2. Okay. Uh, so how did we get this 4 by 6? We just counted the ways it can happen, and that is there are 4 ways you can get x is equal to greater than or equal to 3. Okay. Uh, there are other ways of doing that, and that is called marginalization, and we'll come to that in a bit. So first of all, it should be clear what is joint distribution and what is a conditional distribution. So this is a conditional. This is a conditional distribution. It's conditioned upon z taking certain value. Now, marginal distribution is very related to this, and basically it is the probability distribution of a single variable. So your probability distribution of z is a marginal distribution, which you will calculate using the joint distribution. Okay. So the way to calculate the marginal distribution would be that you would take it as p of y comma z, and you will sum it over all other over the other variable. You will sum it over all values of y, right? So for z is equal to 1, this turns out to be 2 by 6 plus 2 by 6, which is this 4 by 6. Okay. So marginal distribution, marginalization means eliminating all other variables except for the variable that we are interested in. So here marginalizing over y, we will get the probability distribution of z. Okay, that's the marginal distribution of z.